Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everybody. My name is Rafael Irizarry. I am the chair of the section on biology. We're going to focus on genomics and electronic medical records. Our first speaker is Matthew Stevens from the University of Chicago, who has done a lot of work in genomics and also now more recently in functional genomics, where I think this is more related to, where you have often many hypotheses tested. So false discovery rates are a very important part of that, and it's also something that we think is going to extrapolate to many other big data applications. I'll let Matthew Stevens explain this.
Thanks very much, Rafa. Thanks for It's just going to work like that. Great. So before I start on false discovery rates, I just wanted to kind of, one of the things I like to think about is how, by working together, or at least putting our heads together, we can kind of make more progress. And it's kind of obvious in some sense that we ought to be able to make more progress, but it turns out like working with other people to make progress actually turns out to be harder than you might think. And my main experience is actually working with graduate students, let's say, and it always turns out that we don't make as much progress as I expect. But I think some of the tricks that I use with my graduate students to help them make progress may be helpful more generally. So when I first sit down with a graduate student, I don't give them the real problem that I want to solve because it's too complicated, there's too much going on. So you have to like pick out a little bit of the problem that you think they might be up to kind of thinking about and making progress on, abstract the problem to, usually when I'm working with statistics graduate students, abstract it to a problem that they're going to be somewhat familiar with. And then when they've started making progress on that, then we can layer in the complication. And another thing I like to do is to try and early on establish some kind of benchmark that says, if we could do well on this, say, simple simulation, that would be an accomplishment. We'd know we were going in the right direction. I actually think that's kind of another good way that you can measure progress. And you're probably familiar, but communities have set up community benchmarks, like the protein folding community have set up benchmarks. The image analysis communities have set up benchmarks where people come together and work on the same data set and try different methods and compare them. And I think that's been one of the most effective prototypes for people actually making progress together. So I think those are two things you should think about when you're trying to talk to other people and get feedback on your problem. And the last one I want to talk about is recently I've become increasingly aware of the benefits of building what I'm going to call generic tools. So what do I mean by generic tools? Well, here are some examples you've probably heard of: linear regression, k-means clustering, principal components analysis. These are probably not the optimal tool for any given situation, and yet they're really widely used because they're so generic. And the problem I'm going to talk about is maybe not quite as generic as those, but still become pretty generic, is the problem of estimating false discovery rates. And more generally, in this talk, I want to outline, ultimately going to outline plans to develop generic tools for what I'm going to call shrinkage estimation, but I'm going to motivate them first through false discovery rates. So, so here's my abstraction of the generic problem. So in genomics, we often measure lots and lots of things, and we measure them with error. So this results in estimates of lots of effects. So just to give you a simple example, you might be interested in the difference in average activity of a gene between males and females, or between humans and chimps, or between two groups. So beta J here, the effect that you're interested in, is the difference in the activity of gene J. But so you're interested in beta J, but you have a noisy measurement of beta J, which I'm going to call beta J hat, and you've got some kind of measure of its precision, standard error. And the typical analysis turns these things into z-scores or t-scores by dividing the estimate by its standard error, turns those into p-values, and then applies this magic software tool, qvalue, that will give you an estimate of the false discovery rate at any given threshold gamma. So the false discovery rate, for my purposes, I'm just going to give you this Bayesian definition of the false discovery rate, which is the probability that beta j is null given that its p-value is less than the threshold. So the idea is that if you say everything is more significant, everything that exceeds this threshold is significant, and you call it a discovery, the question is what proportion of those things that are significant will be actually false discoveries. So this is an estimate of that quantity. So qvalue is a kind of a generic tool. You just feed it a bunch of p-values, and it spits out false discovery rate estimates. So how does it do that? Well, here's a simple example. So here's a distribution of p-values, and we're trying to estimate, at any given threshold, let's say 0.1, what's the proportion of things that exceed that threshold that are actually false discoveries? Well, we don't know which of these p-values are false discoveries and which are true, but we see a nice enrichment of p-values near 0 compared with the expectation under the null, which is, of course, uniform. So qvalue uses this idea that the p-values will be uniform under the null to kind of draw this horizontal line and say, well, that's what we expect the p-values to look like under the null. So if I draw this vertical line at 0.1, then I can estimate among the findings that exceed this threshold, the area B tells me roughly how many are null, and the area A tells me roughly how many are alternative. And although I don't know which are which, I can estimate the ratio of those areas to get an estimate of the false discovery rate. So you could ask, well, how does it know how high to draw this line? And the answer is, well, it just draws it as high as it can by looking at what's going on over here and just assuming that everything near, essentially that everything near 1 is null. Right? And that's basically as high as it can go. If it can't draw the line here, because then we would have seen more p-values near 1. So that's it, the aim there is to be, quotes, conservative. So I just want to point out that generic procedures have really an outsized impact. So this still astonishes me. The original paper introducing the FDR has been cited over 27,000 times. That's more than 3 times a day for the last 20 years. And in fact, I went to update this yesterday as I was preparing the talk. I last looked a year ago, as it happened. And I think there were over 6,000 additional citations in the last year. So it's nearly 20 times a day for the last year. I mean, it's out of control. Okay, so yeah. Yes. So generic approaches can have value. So let's get in the game and try and develop some generic approaches. So when I look at this approach, I guess I'm going to mention 2 issues that I'm going to actually change in order to, at least potentially in some situations, improve the approach. So the first problem I'm going to call it a problem, is that this previous approach assumed that all the p-values near 1 are null. As I said, that's actually, that never seemed like an unnatural assumption to me. In fact, the way I drew the picture before, it always seemed a very natural assumption to me. So it never bothered me until I started looking at it and I drew this same picture in the z-score space. So you can just draw the same picture in the z-score space and you get this picture. So now I've put the alternative ones on the bottom just so you can see the shape. So the blue ones here are the null z-scores. So they're normally distributed. And these are the alternative z-scores. And what you can see is that, well, there's this big hole in the pattern of the z-score distribution near 0. And it doesn't really make sense. Even if there was an effect, you would sometimes see a z-score near 0 just by chance. And in fact, what I want to claim is that this whole big hole here is really quite unnatural and not what you expect to see in practice, at least under some assumptions. The other thing I'm going to say is that by basically taking this beta hat and a standard error and turning it into a single number, the z-score or the p-value, you're kind of throwing away some information, and particularly you're throwing away the idea that some measurements were more precise than others. So in genetics, for example, you often have some genes that are low expressed and they're harder to measure, and essentially they have a lower signal-to-noise ratio and a higher standard error than the high-expressed genes. And this can cause a dilution of signal. So just to illustrate that, I just did a little simulation where I simulated the effects from a normal distribution, and I had just assumed there were 500 good observations which have a small standard error, and 500 really lousy observations which have a really high standard error. And then if you look at the distribution of p-values of the good observations, you see a nice distribution, and you can see an inflation near 0, indicating some signal. But if you look at the distribution of the poor p-values, you get essentially a uniform distribution, because even though these are simulated under an alternative hypothesis, it's a hypothesis where you've made really noisy measurements, so you have no power, and so the p-values essentially are still uniform. And when you pull these two groups together, you get essentially the bad measurements are diluting the good measurements. So if you ignore that during the analysis, you'll get a different estimate of the false discovery rate, and particularly when you do the analysis of everything, you get a much higher estimate of the false discovery rate, 24%, than if you only looked at the good p-values alone. That is, if you said, look, some of these measurements are lousy, I'm just going to ignore them, which probably seems like the right thing to do if some of your measurements are really lousy. So the idea is that translating your two numbers into one number loses information that some things are better measured than others, and that can kind of dilute your signal. Okay. So, so what are the ideas? One idea is to, instead of using one number, use two numbers for our generic procedure. So instead of having a procedure that's going to take p-values, we're going to take two numbers for each measurement, the beta hat and the standard error. And the other thing I want to do is introduce what I'm going to call a modeling assumption, which is essentially that the true distribution of the effects, the betas, is unimodal about 0. So this is not always going to be true, but I'm going to argue that it's often plausible in settings where beta equals 0 is plausible. Then beta very close to 0 should also be plausible. And in fact, it's often the case, I think, that the larger the effect, the less plausible it becomes. There are a couple of other ways you might motivate this assumption. Another way is that this assumption results in shrinkage towards 0. So any setting where you think it might be appropriate to shrink things towards 0, this assumption that the distribution is unimodal about 0 really kind of fits with that assumption. And another way to motivate it is that it's an assumption that's made almost always in large-scale regression analyses where you're trying to choose which variables are relevant in a large-scale regression. Almost every method out there assumes some kind of unimodal distribution about 0, so a double exponential or a spike and slab, or So it's a modeling assumption that's actually used in similar contexts, but ironically enough, not so much that I've seen in this context. Okay, so just to briefly, the idea, but we're going to approach the problem via empirical Bayes, which is emphatically not a new idea. So Michael Newton, Brad Efron, and his student Omar Muraled-Haran have all, among others, suggested this kind of approach. So, for example, Efron's approach is to take the z-scores and to model them as a mixture of a component that's due to the null, that's the normal 0, 1 component, and a component that's due to the alternative, which he estimates. Essentially, what he does is he estimates f non-parametrically, and then he subtracts this part out in order to leave this part. So he doesn't explicitly model F1. He does a non-parametric estimation of F, and then he subtracts this out to get F1 implicitly. Muralidharan actually explicitly models F1, which is much more similar to what we're going to do. So essentially, we're doing the same thing, except importantly, instead of modeling the z-scores, we're modeling the betas. So the model is that the betas come from a mixture of some which are 0 and some which are non-zero, but come from a unimodal distribution centered on 0. And we're going to estimate this distribution from the data. And the second component is that these are unobserved things we're interested in. Our observations are the beta hats, and we're going to connect them to our unobserved quantities we're interested in through this likelihood. Essentially, we're going to treat the beta hats as our data, and we're going to assume that they have a normal distribution centered on the true value of beta and with this standard error. And we can relax this slightly. We can, say, change to a t distribution, which can be helpful if the standard errors are estimated with small sample sizes. And this is connected to ideas from Valen Johnson and John Wakefield, the idea of basically doing Bayesian inference using just by treating the summary statistic as having this distribution. So I've said we're going to estimate G, and we're going to assume it's unimodal. So a really convenient way of doing that is to assume that it's a mixture of normal distributions all centered at 0, but with different variances. So the way we do this is to just assume that there's a very large number of normals with variances that go from very, very small to very, very big. We just put a large number down, a grid of variances going from very small to very big, and then that only leaves us to estimate the mixture proportions. And the mixture proportions are not actually identifiable because this grid includes components that are kind of heavily overlapping with one another, but the actual estimate of G you get out doesn't depend much on that, and so G is kind of identifiable even though the pi's are not, and it's essentially a trivial EM algorithm to maximize the pi's in this setting. So this, by making the grid finer and finer, you can approximate arbitrarily closely any scale mixture of normals, which includes pretty much everything anyone's ever used in the regression context. But if you want, you can be more flexible by using mixtures of uniforms. So uniforms that start at 0 or are centered at 0 can be more flexible and particularly can capture skew distributions, non-symmetric distributions, which could be important sometimes. So just to illustrate that, here's a mixture of 3. So what we do, right, you could do that. We have implemented a variational Bayes approach that uses a Dirichlet on the weights. But what we do by default, if you like, is to put a small penalty, or well, small penalty that's a bit Dirichlet-like on pi 0. It's the opposite of a penalty, to encourage the weight onto pi 0, and then uniform on the rest. So there are some details which I'm skipping over. Yeah. So, but you don't need to, is the point. You can get the only time it matters is when you start to ask the question: is it exactly 0 or is it very, very small? And so that's what that penalty term is doing, is just encouraging you to answer that question. It's 0, unless you have strong reason otherwise. Okay, so here's a mixture of 3. Well, here's 3 normals, and when you mix them together, this is a unimodal distribution you get out of it. Here's some uniforms. All these uniforms either start or end at 0. So when you mix them together, you get a distribution that's unimodal about 0, but it can be asymmetric now. Okay, so although I've kind of motivated this by false discovery rates, this whole approach actually provides a posterior distribution for each beta. So I guess to be explicit, what we do is we first estimate G, this mixture, by maximum likelihood, combining information across all the observations. And then given G, we can estimate the posterior distribution for each beta J, given beta J hat and its standard error. So because G is unimodal, the point estimates and the confidence intervals all get shrunk towards 0. And because G is estimated from the data, the amount of shrinkage that you end up doing depends on how much signal there is in the data. So if the data say, oh, there are lots of really big effects and very few zero effects, G is kind of flattish, and you don't get very strong shrinkage. If, on the other hand, you give it data that's very null, that looks like noise, then G gets estimated to be very spiky, about 0, and you get very, very strong shrinkage. And similarly, the data points that have a larger standard error get shrunk more than the data points that have a smaller standard error. So for these reasons, we call our R package adaptive shrinkage. So the idea is it's adapting both to the overall signal in the data and to the individual specific measurement errors. So just to show you the results from this approach, this was the results of the qvalue approach effectively, and when we do our approach, you get a very different distribution of z-scores because of our unimodal assumption. And when we analyze these rather naively simulated data with good measurements and bad measurements, when we analyze all the data together, we get essentially the same results as if we only analyze the good ones. And that's because of this likelihood component with the very flat, the observations with big standard error have very flat likelihood and essentially don't change the estimate of G, so they don't change the inference for the good measurements. That's the idea. We actually, if you're sharp-eyed, we actually get a few fewer findings in this particular simulation than qvalue. That's the exception rather than the rule, actually. Oh, okay. My figure disappeared. Okay, so I can't show you the figure, but let me just mention. So, okay, so this figure shows that when you simulate data under various scenarios, we still are conservative in our estimation of the proportion of nulls. So people in genomics are especially worried about being anti-conservative and declaring things to be, to underestimate the false discovery rate. So that doesn't happen except if you simulate a bimodal situation, which of course breaks our unimodal circumstance, then you can force it to be a bit anti-conservative, but it's not too bad. Sorry, the figure didn't come out. Yeah, I made it on a Mac. So you can also ask, well, how well do we estimate the underlying G? And one answer is, well, we do pretty well in the middle. Of course, the tails of G are a lot harder to estimate, so a bit more, we're not quite so reliable in the tails. But a general point is that estimating G is what's known as a deconvolution problem. And Brad Efron talked about trying to attack the problem this way by pretty much the way I've described it, but without the unimodal assumption. And what he reported that essentially he found it very difficult to deconvolve and estimate G. It was very unstable. And one of my points is, if you're willing to make the assumption that G is unimodal, it basically solves this problem of being incredibly unstable and becomes incredibly stable. And that's what this figure shows. Yeah. Okay, last 2 minutes, I'll just mention one problem that arises when applying these methods in practice is that sometimes you start to estimate that there's a lot more signal in the data. This unimodal assumption, which allows for there to be a lot of very close to zero but non-zero effects, has the potential to tell you, sometimes you fit it to data and it fits a G that has very little point mass at 0 but lots of mass near 0. And then when you ask the question, are my findings 0? The answer you get out from your Bayesian calculation is no, because the prior is very weak on 0 itself. It's got lots of mass near 0, but not at 0. And you start to report that everything's likely to be non-zero, even the ones with p-values near 1. So this can be disturbing to a geneticist who's come and, yes?
Don't you want to modify then your questions?
Exactly. So, yeah, instead of asking the question, is it 0, we can ask, for example, is beta positive? Can we be sure which ones are positive and which ones are negative? And in fact, I mean, I'm citing Gelman here, who's the most recent person I've seen pushing this idea. But Tukey, in his 1961 paper, actually says we should be focusing on this question. And the way he says it suggests that there were lots of people at the time would have agreed with that. It wasn't like it was, he didn't seem to be pushing that as a new idea.
The other possibility is to use a non-local prior. And so...
a non-local prior, which means?
So the non-local prior doesn't allow, it smoothly decreases to density 0 at 0, and so it does that.
I see, yes.
And so
that's more what...
having the small signal. So Val Johnson has some beautiful work on that, and it leads to nice solutions. And
okay.
So that would further regularize it.
So that's actually going back to the assumption that there aren't any effects near 0? Yeah. Yeah, I don't like that assumption because I don't think it's...
Smoothly.
I think there are lots of effects near 0. So I prefer to change the question, but yeah. Okay, so I'm not going to go through the summary. I'm going to just mention, because it's a generic procedure, we can apply it to other settings. So one setting we've been playing with is wavelets, where you do a wavelet decomposition of a signal. You get a noisy estimate of each. You can think of each wavelet coefficient as a noisy measurement of the, quotes, true wavelet coefficient, and you can estimate a standard error, and then you can basically apply this kind of approach to shrink your wavelet coefficients. You can also shrink the standard errors. I've kind of fixed all the standard errors and treated them like they were God-given in this. But actually, if they're estimated using only a small number of observations, we believe it's actually important to shrink the standard errors as well. And, okay, I'm out of time, but we're working on multivariate versions, and also everything I said assumed everything was independent, but we'd like to be able to allow for correlations before. And I'll leave my slide up there with acknowledgements and take any questions. Thanks very much.
Any other? Oh, go ahead.
So it sort of seems extremely similar to the stuff on like compound decision problems and normal means. And so
it's
like
basically
Larry
normal.
Brown and like Conquer and Mishra have a really fast algorithm for doing approximate non-parametric maximum likelihood estimation of G.
Yeah.
And that stuff seems to work pretty well, particularly if you're going to do an interval instead of fixating on the point mass. It would be good to compare.
Yeah. So what the stuff I'm aware of assumes all the variances are equal for that. They are working on non-equal variances. I'm not sure it is, but if you could point me to the most recent thing.
Okay.
Yeah, I'm aware that they're doing fully non-parametric stuff rather than without the unimodal assumption. And when I've tried that kind of approach, not specifically theirs, it's very delicate, which is basically what Efron was reporting. You end up getting very spiky non-parametric distributions for G with point masses on things away from 0 that you probably don't really believe, but are the non-parametric maximum likelihood estimate.
You instead use some particular mixture of Gaussians, but isn't non-parametric.
Okay.
Unimodal.
Okay.
Great.
I have one quick one. This using normal assumptions. What about
Yeah.
negative binomial?
Yeah. So the original. So you're talking about the likelihood, right? The normal likelihood. Yeah. So the idea is that we're making a normal assumption for the beta hat rather than for the data. So if you can fit a generalized linear model, if you've got enough data points, you might believe that the beta hat is approximately normal. But we're currently working on, testing how well it actually works on RNA-seq data, particularly when you've got smaller sample sizes. It's a bit more delicate. So yeah, it's a great question. We're working on it.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.